So in the last video, we solved the same system in the case of a frictionless surface. If you haven't watched that video yet, you should stop this and go back and watch it. But we solved this in the case of a frictionless surface. But now we're going to solve it in the case of that it is accelerating. M2 is accelerating downward, M2 is accelerating to the right. But now there's a coefficient of kinetic friction between this surface and mass 1. So I've drawn the free body diagrams, except I forgot to label the normal force. I've drawn the free body diagrams, which look exactly the same as the previous problem. Right, they're the free body diagrams, with the exception of that now on M1, I have this force of kinetic friction. Here there was nothing because there was no friction, but now I have a force of kinetic friction pointed in what I've called the negative x direction. You can call it positive or negative as you please, but I've defined to the right as positive here, x, and which means this is to the left, which is negative. Similarly over here, similarly for coordinate system, down is my positive x direction. I've done that to couple up these systems. Okay, so we're going to do the same thing we did before, which is to solve for the accelerations of the blocks. Now, though, I've got kinetic friction, and if I remember, kinetic friction has a value equal to this coefficient of kinetic friction, which I'm going to assume that I know for this problem, times the normal force. So that's going to be the normal force acting on M1, which is here. So before, I didn't have to worry about the y direction for M1 at all. There was nothing happening of interest to me. But now I do. Even though in the y direction, this is still not coming off of the table, it's still not accelerating in the y direction, I need to determine the normal force to be able to characterize the frictional force. So there's crosstalk between the x direction and the y direction. So let me do that. Sum of the forces in the y direction is equal to ma sub y. And as I said a while ago, M1 is not coming off of the table. It's not crashing through the table. It's not accelerating in the y direction at all. In fact, it's in equilibrium in the y direction, which makes my job easy. I get the normal force minus m1g, that should be subscripted, is equal to 0. Therefore, the normal force is equal to m1g. Now I'm going to go still on block 1. I'm going to solve this in the x direction. I'll do it underneath. This is M1 still. Well, I have tension minus the kinetic friction force is equal to M1A sub x. It's not in equilibrium, so I can't cross this out. What I can do is substitute in for the friction force from here. Friction force is equal to mu k times the normal force, but I have determined the normal force already as m1g, so it looks like in this case I'm going to get mu k times m1g, right? This is the normal force. So that's what I'll write here. T minus mu k m1g is equal to m1ax. All right. That takes care of, or at least for now, takes care of block 1. Let's look at block 2. The calculation here should look really exactly the same as in the last video, because I have nothing else going on in this one that I didn't have in the last one. So what do I get? I get m2g minus tension is equal to m2a sub x. That should be subscripted. So I have these two expressions which involve my two unknowns, the acceleration and the tension. I want to know the acceleration, so I want to eliminate the tension. So I'll call this equation 1. I'll call this equation 2. I'll do a little work here. So let me solve equation 1 for tension. I'm just going to move the friction term to the other side. Equation 1 gets me tension is equal to m1ax plus mu k m1g. Equation 2 gets me that, if I rearrange this for tension, I'm going to get tension is equal to m2g minus m2ax. I'm going to invoke the transitive property and set the right-hand sides of these equal to each other since they're both equal to the same tension. I'm going to need to cut cut that off. M1 AX plus mu K M1G from here is equal to, I'm not going to have room, M2G minus M2AX, just barely. Now I'm going to get all my acceleration terms on the same side. I'm going to get M1AX from here plus M2AX is equal to M2G minus, moving this over, minus mu K M1G. I'll move down here where I have more room, do some factoring. I get AX times this additive term M1 plus M2. I will factor out a G here, equals G times M2 minus mu K M1. Now I can solve for the acceleration. I'm gonna put the rate, I'm gonna divide the parenthetical term here by the parenthetical term here. I'm gonna put that first so I can compare it with my previous answer a little bit easier, because the previous answer I put it first. What I get though is this, a sub x is equal to this parentheses, M2 minus mu K M1 divided by M1 plus M2 G. All right, so again, let's see if it matches up with my expectations. M1, M2, and mu K are all positive, so there's no way this ratio, this coefficient can be greater than 1. It's always going to be less than 1 because the denominator will always be larger than the numerator. So this will always be less than G, which is exactly what I expect. If I look at this free body diagram, I have to recognize that this is subject to more forces than just gravity, right? It's M2G minus tension. So I'm looking for the acceleration to be less than G, which it is. The same thing happened in the other problem that I solved. However, the other problem didn't have friction. So let me just compare these two answers. This is what I got for the acceleration in the case of the frictionless surface. This is what I got for the acceleration in the case of the surface with friction. Maybe I'd cover that up so you can see it better. Yeah, I think it's fine. Let's see if we can convince ourselves of a couple things. What do we expect when we put in friction? Do we expect the acceleration to increase? I certainly hope not. I expect it to decrease, right? Friction is going to be making it harder for gravity to do its job. So look at this. Can we convince ourselves that this term is less than this term? M2 minus mu K M1 is always going to be less than M2. The denominator is the same. So if this numerator is always going to be less than this numerator, then what that means is that this acceleration is always less than this acceleration for equal masses, of course. And that makes sense. We get something very similar, but now I have this friction term. And notice it's subtractive. The acceleration is lowered. The acceleration here is lowered by the advent of this friction term. So this makes some sense physically. Hopefully it now makes a little bit more sense mathematically. That's what friction does. It messes with your forces. It makes it harder to accelerate your object. That's not always true. But it definitely always opposes the motion and throws in terms. I will point out again, you have this additive term in the denominator, which is what you should expect from coupled systems. I'm moving both masses, and so I should expect a term down here, or I should expect terms somewhere that involve the addition of the masses. I get it here, just like I got it in the frictionless case here. So it's just something to look for.